Now this is the topic electric field due to a uniformly charged thin spherical cell. This is our spherical cell. Spherical cell, it will be hollow from the inside. We have charged uniformly. So this is the important topics we can use here to find electric field from a distance r from the center of this spherical cell. The center of the spherical cell O, and r is its radius, and we have given some charge which uniformly distributed over this surface. Now the surface charge density, if I say that sigma is the surface charge density, surface charge density so it means that charge divided by area. So suppose if I say that the charge is total charge Q is given to this uniformly spherical cell, its surface area will be 4 pi r square. This will be our formula. Now since electric field lines of this charge distributions radially outwards, so radially outward, these are the electric field lines which goes radially outwards. So we have to find out that what will be the electric field inside of this cell and outside of the cell. Let us suppose to calculate electric field at some outer area, outer region, the P point where we need to calculate its electric field. Since this is a symmetrical Gaussian surface, we have taken this symmetrical Gaussian surface which is in spherical shape, Gaussian spherical. This is called Gaussian surface. So this is symmetrical. Since it is at a distance of r, at every we know that at every point of the spherical cells is at a distance of small r. So the magnitude of electric fields on every point of this cell whose radius is small r is the same. Now we can use Gaussian law. So by the Gauss's rule says that total electric field is equal to total charge inside of this Gaussian surface divided by epsilon naught. Total charge divided by epsilon naught. Total charge inside of this will be sigma times of area. Sigma is surface charge per unit area. If you multiply it by the area, so we will get the total charge inside of this Gaussian surface. It will be 4 pi r square divided by epsilon naught. So this comes out from the Gauss's theorem. Now using the electric flux formula, we know that now take a small area on the surface of the Gaussian surface, suppose and flux pass through this one. Electric field will be radially outwards, and area vector is also, suppose area is ds. So EDS will be in the same direction, therefore so electric flux pass through this one E dot ds. Since angle between E and ds is 0 degree, therefore it comes out E ds cos 0 degree. Cos 0 degree has the value 1. Now it comes out E dot ds. So now total flux pass through this whole Gaussian surface. We have to integrate this one. total electric flux will be d phi a, E times of ds. E is taken out, and now the total area of this Gaussian surface will be the surface area. Mathematically we can calculate it 4 pi small r square, 4 pi small r square. Now this is equation number 2. Using equation number 2 and equation number 1, so we will be able to find the electric field at the point of P. Yes. So now using equation 1st and 2nd. Now equation number 2nd comes out E times of, from 2nd and 1st 4 pi r square. Total flux phi a. Phi is also this one. Sigma times 4 pi. Sigma times of 4 pi r square will be small q. So here it should be this one, sigma times 4 pi r square will be capital Q. Now this electric flux comes out capital Q divided by epsilon naught. Therefore E is equal to 1 upon 4 pi r square times Q divided by epsilon naught. Now rearranging this, 4 pi epsilon naught times Q divided by r square. This is the formula. This is the electric field at outer point. The formula for outside of this cell. Outside of the cell, so the field at the point of P behaves like the total charge of the spherical cell, suppose concentrated at the center of the spherical cell. This this seems that the total charge on this cells is concentrated at the center of this spherical cells, and this cells acting like a point charges, and you know that point charges, the electric field due to point charges at a distance of r is equal to 1 upon 4 pi epsilon naught Q upon r square. Now the second case, we have to calculate the electric field inside of this spherical cell. Now in our case number 2, when the point to be inside of this one, inside of this spherical cells. When the point P is inside of the cell, So this is the point where we need to calculate electric field due to this spherical cell. So electric field should be radially outwards, because I have given this is positive charge. This positive charge is uniformly distributed over this one. So this is the Gaussian surface. This is our Gaussian surface, and whose radius small r. We need to calculate electric field at the point of P. Take a small surface area. Suppose take a small surface area on this Gaussian surface, and whose area vector is acting outwards. Since electric field is also in the same direction, our electric field is also radially outwards. This is the radially outwards. Therefore E and ds will be in the same directions. Now flux pass through this small area. This is the area vector. Now d phi is equal to E dot ds. Since the angle between E and ds is 0 degree, this comes out E ds cos 0 degree. Cos 0 degree has the value 1. Total flux passed through this Gaussian surface. This is our Gaussian surface. Gaussian surface. This is a imaginary hypothetical. So now total flux passed through this Gaussian surface. We should have to integrate this one. Now total flux phi e is equal to integration of d phi e integration of ds. Since electric fields at the same distance from the center of will be same in magnitude but different in the directions, because electric field at this p point will be along this right. If I calculate the electric field at this point, it will be away from this one, but its magnitude over this Gaussian surface will be 0 if there is any electric field. So E is taken out here. If I take E out, E is outside. Integration of ds. We know that integration of this whole surface is equal to 4 pi r square. So it comes out 4 pi small r square. Now this is the equation number first. Now we can apply the Gauss's law. Gauss's law over this surface area. Now using the Gauss's rule, by the Gauss's law, we know that the total electric flux through a Gaussian surface. This is our Gaussian surface. Gaussian surface got total charge. Total charge inside of this one. So charge divided by epsilon naught. Charge upon epsilon naught. We already defined the surface charge density of this spherical cell is charge upon 4 pi r square. So 4 pi r square. Since there is no charge inside of this one, because our charge resides in this cells, because there is no charge inside of this one, so our charge becomes 0 over this, inside of this Gaussian surface. Now 0 divided by epsilon naught becomes 0. Now from equation number first, if I put the value of phi at this point, I will get the electric fields which comes out 0. So now from equation 1 and 2, if I equate equation first and second, it comes out E times of 4 pi r square is equal to 0. From here, the electric fields at the point of P, which is inside of the cells, will be 0. So we can say that very easily we have calculated this tedious electric field finding at outside and inside of this spherical cell. So by using the Gauss's law. So now we have to draw the graphs between the electric fields and the distance from the center. Electric field intensity and distance from the centers. This is the graph E versus of R. R is the distance of the point P. R is the distance of the point P from the center of O. So we know that inside of this Gaussian, inside of this spherical cell whose radius is capital R, the electric field equal to 0. There is no electric field inside of this cell, but outside there is electricity which is not equal to 0. So the outside we have already know that for the outside electric field has the value 1 upon 4 pi epsilon naught, and charge which contained this spherical cell divided by the r square. So for the outside we have the formula E upon r square. This is the case for the outside. For the outside, this is the parabolic. This is the parabolic questions. It is parabola's questions in E and r square. Therefore, this should be like this. So inside of there is no one. So on the surface it has the maximum electric fields. Maximum electric field should be at the surface of this one. And if I goes away from the center of this spherical cells, our electric field should go on decreasing. Yes, it has a maximum value. That maximum value comes out here 1 upon 4 pi epsilon naught total charge divided by capital R square. So this is the maximum value. So this is a graph between E and R.